In this module, we will discuss inference on two variances. This will be in the form of a hypothesis test and confidence intervals. This will be similar to what we did for means. Let's start with the potential sampling distributions. When we did this for two sample means, it was somewhat easier because the distribution of a linear combination of two means based on them coming from a normal distribution is pretty straightforward. If we assume that the independence holds, the sampling distribution itself of the combination is normal. This does not work for variances. We still need to find a combination of the variances that we can easily determine a sampling distribution for that still represents equality. Unfortunately, the difference being 0 will not work. So what will? Another way that we can represent equality is with the ratio being equal to 1. What we will do is take the quantity that we know has a known distribution, like the ratio of n minus 1 times s squared divided by sigma squared, and find the ratio of this quantity for both samples. This work has been done for you on the slide. We can now write the null hypothesis for this case as the ratio of the two variances equal to 1. If we look at this in more general form, we can write it as the ratio of the two variances equal to some constant f sub 0. Now we can use the f distribution for this test. The ratio of two chi-squared distributed random variables over their degrees of freedom follow an f distribution with nu1 equal to m minus 1 degrees of freedom and nu2 equal to n minus 1 degrees of freedom. We refer to these as the numerator and denominator degrees of freedom respectively. Also, notice the inverse property that is shown on the slide. It will come in handy later. The f distribution is very similar to the chi-square distribution in that it is skewed right and can only take on positive values. This makes sense considering that it is a ratio of two chi-square values that can only take on positive values. Now let's put this together to get the f-test. Now the two-sample f-test is based on the ratio of two sample variances. We see here that the alternatives are typical. Just as with the chi-square distribution, it is important to note that the f distribution is not symmetric. So we can see that we must be careful in finding critical values. Now let's look at an example. Here we have a problem where a company would like to compare supplier thickness variances. They would like to know if there is a difference in the variances. Usually this kind of thing is done when a company may want to switch suppliers and would like to see if one is any different from another. Let's look at assumptions. For this problem, we assume that the sample size per group is equal to 15. We will also use alpha equal to 0.1, and the alternative will be that the ratio is not equal to 1. The sample variances are 10.57 and 6.93 respectively. To see the solutions, look at the file called Two Sample Variances Example 1. Now let's look at the conclusions. Statistical conclusion. Since 0.1261 is greater than 0.1, we will fail to reject the null hypothesis. We find that there is not enough evidence to conclude that there is a difference between the variances. Now, for the real-world results. There is not enough evidence to conclude that the supplier's variability and thickness are different. Now let's look at confidence intervals. Just like with the means, we can build a confidence interval for the two-sample situation. We will do this by working from the sample distribution of the ratio. Let's start out by looking at the acceptance region. For this situation, we can get the probability statement from the slide. We will use this to get the acceptance region. We do this by removing the probability operator. Now that leaves us with the acceptance region. We can rearrange things to get only the ratio of the population variances in the middle. Now we find the 1 minus alpha times 100% confidence interval for the ratio of the variances based on what is in the slide. Remember that the critical values are based on leaving the probability to the right of the value. Now what about confidence bounds? Just like with the sample means, we can get a one-sided bound for the ratio, the variances. Just like with the chi-square distribution, the ratio will never be negative. This means the lower bound for a one-sided upper confidence bound will usually be 0. Now we can look at the ratio of the standard deviations. Now, what do we do with the ratio of the standard deviations? Usually the results from a hypothesis test for the variance hold for the standard deviations as well. Now for the confidence intervals, we can just take the square root of the bounds. Remember that once you find the interval values, They are just constants and we can do whatever we want to them. Let's try an example. We are given the summary data from a study on the compression strength of two different types of boxes. We would like to create a 90% confidence interval for the ratio of the variances. Let's look at the assumptions. We will assume here that alpha is equal to 0.1, the sample sizes are 10, and the sample variances are 27 and 41, respectively. Let's take a look at the solutions. The solutions can be found in a file called 2 Variances, Example 2. Let's look at the conclusions. We interpret the confidence interval as follows. We are 90% confident that the true variance ratio is somewhere between 0.7254 pounds and 7.33 pounds.